On page 22, integration by substitution. So the idea here is that you're going to choose some value or expression that can be replaced by the letter u, which in turn is going to allow us to replace all aspects of x within the integrand. Alright, so I'm going to walk you through the process. I mean, it's all detailed here, but it's essentially thought of as a sort of a reverse of the chain rule, right, for differentiation. So what we like to do is choose generally the more complicated part of the expression to designate as u, right? But really a better way of thinking about it is to say that I want to choose an expression whose derivative is just a constant multiple away from being the other expression. All right, so you have multiple factors that make up your integrand. So in this case, you have two factors. You have the 2x and you have the x squared plus 1. What I want to do is I want to choose an expression to call u whose derivative would be a multiple away from being the expression that I did not select. All right, so what I'm going to do here is select x squared plus 1. So I'm going to let u equal x squared plus 1. What we do is we differentiate that, because I can swap out the x's for u's, but I still also have to swap out the dx as well. All right? In order to do that, I have to take a derivative. So I'm going to take the derivative of the u equation with respect to x, so du dx is going to be equal to 2x. All right? But what I want to be able to do is swap out anything that I didn't call u, aside from any constants or constant multiples, swap out anything I didn't call u with an expression that involves whatever I come up with here. All right. So looking at this, I see, and I like to use a highlighter, helps to keep it organized in my mind anyway. So I have, this is what I'm calling u. And you know, some people like to do it kind of a piece at a time, just kind of take inventory of where they are in the process. So let's say I have my integral. I'm going to replace this with a u. I still have my 2x and my dx. Those have to go. I mean, I'm not as concerned about the 2, but the x and the dx have to go. All right. So what I want to do is I want to use this relation here to help me accomplish that. All right. So what I'll do is I'll take my differential equation du dx equals 2x, and I'll put it in differential form by multiplying both sides by dx. So that's going to give me du equals 2x dx. And if you look at it, you realize, oh, wait a minute, that's exactly what I need. 2x dx, that's equivalent to u. All right, if I just do a little rearrangement, now you can feel free to do this part in your head, but I'm going to do it on paper, digital paper. I could rewrite this as u times 2x dx, which would allow me to swap out the 2x dx for a du. Which is a nice clean substitution. Doesn't always play out that way. Most of the time we got to manipulate our differential equation, but in this case we got lucky. You know, slash it's number 1. You know. So what I do is I integrate this with respect to u, because it's all exclusively in terms of u. So increase the exponent by 1, you know, the understood exponent of 1. Increase it by 1, divide by the new exponent, tack on a plus c. Much easier to take the integral in this form than it was in the previous form. All right, so mission accomplished there. Not our final answer, because our original question was posed in terms of x's. So our answer has to be given in terms of x. Fortunately, we have a relation between u and x. U is the same as x squared plus 1, so I'm going to replace the u with an x squared plus 1. And so that's our antiderivative. You know, you get to a point where you get enough experience with this stuff, you start being able to do it in your head. But until you get there, this is a pretty good strategy. You know, different people learn it in slightly different ways. But this is the way, you know, I tried it in different ways over the years. When I was a student, I went with good old guess and check. And that got me only so far. But then as a teacher, you know, I went with different approaches. And this is the way that I kind of settled on as probably the way that met the needs of the far majority of the students. So let's take a look at number 2. I can look at this as two separate factors, x squared and the root of x cubed plus 1. All right. I could also look at it as x squared and then the composite function of x cubed plus 1 plugged into the cube root function. All right, in which case I would let u be equal to x cubed plus 1. Now, there's different schools of thought on this. What a lot of people will do, at least when in the early going, is they'll say, well, I got a bunch of different possibilities that I can allow to be my u. I'll just try one, and if it doesn't work, I'll try something else. You know, you do want to be strategic about it because you don't have all the time in the world. So you probably don't want to select u equals x squared because, again, the main criteria here is whatever you select as u has to differentiate in such a way that it'll be a constant multiple of whatever you didn't select as u. So if I take the derivative of x squared, I'm going to get a 2x. That's not a constant multiple of the square root of x cubed plus 1. All right. Now, if I go the other, you know, to the other extreme and select u equals the square root of x cubed plus 1, you know, just kind of play it out in your mind, I'm going to get as a derivative 1/2 x cubed plus 1 to the negative 1/2 times 3x squared. If I simplify that, or even if I simplify that, I'm not going to get a multiple of x squared. All right, so it's got to be something else. As it turns out, if we let u equal x cubed plus 1, you know, not the radical, but the radicand, the thing under the radical, then we're going to be in good shape because I can take the antiderivative of the square root of u. That's not a problem. I don't have to replace the entire thing with a u. If I want to replace part of it with a u, that's fine. I wouldn't want to let u equal x cubed because then I'd have to take the antiderivative of the square root of u plus 1, which is a little bit more complicated. It's still doable, but a little bit more complicated. Here, not too bad. Du dx is equal to 3x squared. Now, you can probably skip this step and go right to du equals 3x squared dx. The reason I say that is, you know, if the second step after you take the derivative is to just multiply both sides by dx, then why not just do it all in one shot? All right. So kind of stop and take stock of what you've done. What have you done? We replaced the x cubed plus 1 with a u. So now I have a radical u. I got an x squared and a dx left over. Those have to go. But see here I have a 3x squared dx. Well, I don't want a 3x squared dx, I just want an x squared dx. So let me divide both sides of my differential equation by 3. So 1/3 du is the same as x squared dx. So now I have the ability to make a clean substitution. And like I said before, you could show the intermediate step where you move things around, or you could just kind of skip that. I'll do it this one last time, and then I'm going to start skipping it. So the square root of u x squared dx. And in fact, there is one step I'm going to kind of merge here. Instead of writing the square root of u, I'm going to start writing it as u to the 1/2, just because I want to be able to use a reverse of the power rule. All right. So I'm going to have a 1/3 and a du replacing the x squared dx. Move some things around. 1/3 u to the 1/2 du. Increase the exponent by 1, u to the 3/2. Divide by the new exponent. Dividing by 3/2 is the same as multiplying by 2/3. So 2/9. Oh, why did I do that? Nobody knows. Plus c. So then I just have to reverse substitute. Or just substitute, really. X cubed plus 1 replaces the u. So 2/9 x cubed plus 1 to the 3/2 plus c. And that's all she wrote for that. All right, so all of that for that one antiderivative. Now, you could see in some cases it'll seem more complicated, in others it'll seem simpler, but you know, they're all u substitution cases. They're all in the same, same vein. So looking at number 3, hopefully it should seem to get a little easier if I let u be equal to x cubed plus 1. All right, so it's the same u, and it's actually the same thing to cancel out. All right, so actually I'm gonna undo that, and I'm gonna get a little crazy here. I'm gonna say, yeah, you know what, you're coming with me. Because I could swap this out with a u, and I can swap this out, the x squared dx, with the 1/3 du. Clean it up a little bit. We're looking at, I'm going to actually pull the 1/3 out of the whole thing, because it's constant multiple. Put a little too much pizzazz at the end of the tail of the u there. So I got a radical integral of 1/u du. I wanted to write it like that because I wanted to make it painfully obvious that this is a natural log situation. Which requires the natural log rule. All right, and so now I can reverse substitute. And there it is. All right, so once you start seeing the potential candidates for u, it gets a little easier to get started on a problem like this, or problems like these. Like in number 4, I'm inclined to call u 1 plus x to the 4th, because the derivative of x to the 4th is 4x cubed. That's going to help me cancel out the x cubed. All right, now you'll see here that I have the clean cancellation of the 1 plus x to the 4th. I don't have a clean cancellation of the x cubed dx unless I divide both sides by 4 here. So 1/4 du is equal to x cubed dx. So now I have the ability to cancel out cleanly. So for this one, I have a u squared on the bottom. That's not a natural log, because I can bring that u squared up and make it u to the negative second and use the reverse power rule. So increase the exponent by 1, divide by the new exponent, and then do my substitution to bring the 1 plus x to the 4th right on back in. Placing the u and there it is.